Welcome back, class. Today we are going to discuss the topic of what is called the least common multiple, otherwise known as the LCM. The LCM, or least common multiple, is a property that exists between two or more numbers on the number line. So, for example, if you take the number 10 and the number 15, and you look at the number 10 that is being multiplied sequentially by a given number. So 10 times 1 gives us 10, 10 times 2 gives us 20, 10 times 3 gives us 30, so on and so forth. And then you look at the number 15 that's being multiplied sequentially by some value. 15 times 1 gives you 15, 15 times 2 gives you 30, 15 times 3 gives you 45, 15 times 4 gives you 60, so on and so forth. What you begin to realize is that there exist what are known as common multiples between these numbers. So 10 times 3 gave you 30, 15 times 2 gives you 30. We would call that a common multiple between 15 and 10. We would also call 10 times 6 or 60 and 15 times 4, which is also 60, a common multiple because they seem to overlap. And then when you get to 15 times 6, which is 90, and 10 times 9 is equal to 90, that would also be a common multiple. And in fact, as you go down the number line and you're multiplying 15 by ever greater terms and you're multiplying 10 by ever greater terms, there will be an infinite number of common multiples between any two given values on the number line. Now, it so happens that the smallest common multiple, otherwise known as the least common multiple, or LCM, between two numbers has some interesting properties that we want to hone in on, not just for this class and for the sake of number theory, but for the sake of being able to solve more extensive and or more complicated algebra expressions in the future. Okay, so just a definition. We'll provide a rigorous definition of an LCM. A common multiple of two numbers, we'll call those numbers A and B. I don't know what A is, you don't know what A is. I don't know what B is, you don't know what B is, but these are just two numbers, may be defined as any situation where if we took a number and we multiplied it by A, and we take a number and multiply it by the second value B, there exists some sort of an overlap, or said another way, these numbers actually equal the same thing. So for example, 15 times 2 gave you 30. 10 times 3 gave you 30. So at that point, your n times your a, your some number or value that you're multiplying with your first number, and some number or value that you're multiplying with your second number were the exact same thing. We'll also say that this n and m value need to be whole numbers. So for any whole number n and m. So these have to be whole numbers. So you can take any whole number, n and m, and if you multiply n with some number a, and I multiply m with some number b, and they happen to equal the same thing, we'll call that a common multiple. Okay. So then now we can define a least common multiple in a rigorous manner. We'll say that the least common multiple of two numbers A and B uses the following notation. So the LCM of A and B is the smallest multiple or common multiple of any two numbers A and B. So that is the rigorous definition of an LCM. Now, there are a number of different ways to find the least common multiple, one of which that is used by the computer system online, the MyLab Math system that we're using at the college, is called the list method. And with the list method, as the name implies, if you wanted to take the least common multiple between two numbers, we're just going to list out the multiples of those two values until we find the first time that the numbers overlap. So just as an example, suppose I wanted to find the least common multiple of, say, 4 and 12. Okay? I'm going to denote finding the least common multiple of 4 and 12 using this notation. Okay, I'm just going to write LCM parentheses 4 and 12. And what that means for me to do is, in this instance, if I'm using the list method, I'm just going to go to the side of my paper somewhere, and I'm going to take my number 4, the first value inside of this sequence of parentheses, and I'll multiply it by different numbers in sequence. So I'm going to start by multiplying 4 with 1, giving me 4, and then I'll multiply 4 with 2, which should give me 8, so on and so forth. 4 times 3 gives me 12. 4 times 4 gives me 16. 4 times 5 gives me 20, so on and so forth. And you can kind of keep doing this up the number line, if you will. And then I'm going to take my second number, 12, and I'll do the same thing. I'm going to take 12, I'll multiply it by 1. That gives me 12. I'll take 12, I'll multiply it by 2. That gives me 24, so on and so forth. Now, here's the deal. Here's the deal. Even though there is a common multiple between 4 times 6, which gives you 24, and 12 times 2, which gives you 24, we are looking for the least common multiple, or the lowest multiple that exists, which would be 4 times 3, giving you 12, and 12 times 1, giving you 12. So the LCM of 4 and 12 is going to be that first common multiple, 12. Okay? One of the interesting facts about least common multiple is that if A and B are prime numbers, then the LCM of A and B will just be A times B. That's all you're going to have to do. So if A and B are both prime numbers, to find the LCM, you don't necessarily have to list out the multiples. You could if you wanted to, but it turns out that because of the properties of the LCM itself, the LCM of two prime numbers is just those two values multiplied together. So as an example, suppose you wanted to find the LCM of 7 and 11. Well, first of all, 7 is a prime number, 11 is a prime number. If we knew in advance these were prime numbers, all you would have to do is take 7 multiplied by 11. That would give you 77. Another example, suppose I wanted to find the least common multiple of 3 and 13. Because 3 is a prime number, 13 is a prime number, all you have to do is do 3 times 13, which gives you 39. Finally, LCM of 5 and 17. Both of these two numbers are prime, so you just take 5, multiply it by 17. You're going to go to the side of your page somewhere. 15 times 17, 5 times 7 gives you 35. Carry the 3, 5 times 1 is 5, plus 3 gives you 8. Drop your 0, 1 times 7 is 7, 1 times 1 is 1. Add everything down. 5 plus 0 is 5, 8 plus 7 gives you 15. Carry the 1, 1 plus 1 is 2. And you are stuck with 255. I'm sorry, I did 15 times 7. My bad. It should have just done 5 times 7. Should have been 85. My bad. Add an extra 1 in there. 85, backing up. There we are. Okay. Now, while it's true that we could have used the list method for finding an LCM if the LCM is not prime, the list method is often, in reality, impractical, okay? Because it may take you a very, very long time to actually find the multiples of any two numbers, even if those two numbers are relatively small, such as a two-digit number. So, just as an example, suppose you were to try to find the LCM of 48 and 74. Now, 48 is not necessarily a very big number, and neither is 74. But it would be kind of a pain in the butt to have to list out all of the multiples of 48. It's not to say that you couldn't do it, right? So 2 times 4 would give me 8. 2 times 8 gives me 16. And so you would have 80 plus 16, which should give you what, 96? Um, but it would be rather labor intensive, if you will, to list out all of these multiples, especially when you don't know where the least common multiple is going to exist. It may take me multiplying 48 by 30 or more terms before I find an LCM of 48 and 74. And similarly, I might have to multiply 74 by 15 or so terms in order to find the least common multiple with 48. And so I don't know. It's not that you can't do it. It's just going to be very time consuming. And so instead of doing the list method, there is in fact a better way to find a least common multiple, and that is using a prime factorization method, or the prime factorization method rather. All right, so to find the LCM using the prime factorization method, we must do the following. We must first of all list out the prime factors of 74 and 48. We can do this using a factor tree diagram. That's usually fairly simple. So you're going to try to figure out what numbers divide into 74. Note that 74 is an even number. It's an even number because it ends in a 4 in this instance, and 4 is an even number. So we would say 74 is an even number. And what that tells you is you can definitely divide 2 into 74. So let's go to the side of our page somewhere. We're going to take 2. We'll divide it into 74. 2 goes into 7 3 times. 3 times 2 is 6. We'll subtract. 7 minus 6 gives you 1. Drop your 4 down. 2 into 14 goes 7 times. 7 times 2 is 14. Subtract, you get 0. All right, so you have 2 and 37. Now, I happen to be aware that 37 is a prime number, but you could check this by trying to divide 37 by a number of terms. You know, try to divide it by 17, try to divide it by 13, try to divide it by 23. None of these numbers will divide 37. And so at some point, you will eventually find that 37 is in fact prime. Okay, so moving on to 48, this is pretty much all we can do for 74. But if we look at 48, 48 is also prime. And you'll find that 2 is going to go into 48 exactly 24 times. 2 goes into 4 2 times. 2 times 2 is 4. 2 goes into 8 4 times. 4 times 2 is 8. So you will see that 2 times 24 gives you 48. 24 is itself a even number, so we can divide 2 into 24. 2 times 12 gives you 24. 2 times 6 gives you 12. 2 times 3 gives you 6. All right, and so we now are left with our factor tree diagram. So all we have to do at this point is we're going to list out our prime factors. I'm going to take my number 74. I'm going to write it to the side of my page. 74 is the same thing as 2 times 37. And guys, I want you to do this. For all of the problems, I want to see this on your paper, okay? Because this is just the easiest way to perform the LCM. You're going to give yourself some space. I usually draw a box to the side and I'll label it LCM to keep track of what I'm trying to do. And all you're going to do is you will cross out any multiples that you have in common, any what are called common prime factors between 74 and 48. So 2 would be a common prime factor between 74 and 48, and I will list it exactly once here. I should also have another number, maybe. I do not have another number. Okay, so I've got 2. That seems like it's pretty much it. Now, all you have to do with an LCM is you're going to look at what you don't have here. So I'm missing a 37. I'll underline it and write it once. I'm also missing a sequence of 2's that are going to be multiplied by my value, 2 times 2 times 2 in this instance. And I'm missing a 3. So we've got to multiply all of these numbers together and figure out what that is equal to. And that is our LCM, simple as. Okay. So there are a number of different ways I could do this. I could use the commutative law and rearrange my terms. I could go 2 terms each. I probably will go 2 terms each. 2 times 2 gives you 4. 2 times 3 gives you 6. And 2 times 37, I'll go to the side of my page. 37 times 2, 2 times 7 is 14. Carry the 1. 2 times 3 is 6. Plus 1 gives you 7. So I have 74. All right, so now I have 74 times 4. 4 times 4 is 16. Carry the 1. 4 times 7 is 28. Plus 1 gives you 29. So I've got 296 times 6. 296 times 6 will be 6 times 6 is 36. Carry the 3. 6 times 9 gives you 54. Plus 3 gives you 57. Carry your 5. 6 times 2 is 12. Plus 5 gives you 17. So we will have exactly 1776 at the end of the day. And yes, it would have been a massive pain in the butt to get up to 1776 from 48 and 70 and 74 as well. So what we've determined is the LCM of 48 and 74 is 1776, and that will be all we have to do. Let's try some better numbers maybe, though. Let's calculate the LCM of 144 and 180. These two numbers are relatively large, so we would assume at first glance that the LCM is going to be rather massive as well, or potentially it could be rather massive, as if we were to multiply, say, 10 by 180, we would already be into the thousands easily. And so we really would want to avoid the list method for this particular problem statement. And so to that end, we are going to, again, use the prime factorization method in order to calculate our LCM. I'm going to list out a factor tree diagram for 144. So go ahead, go to the side of your page, write down 144, and just know that 144 is the same thing as 12 times 12, guys. So 12, of course, is 6 times 2. 6 is 3 times 2. 12 is 6 times 2, and we have 3 times 2, and we have our factorization diagram. We'll do the same thing for 180. Note that 90 times 2 gives you 180, 45 and 2 gives you 90, 5 and 9 gives you 45. We have 3 and 3 gives you 9, rather. All right, so once you have your factors, you're going to go to the side of the page. You're going to write out your prime factorization. It doesn't matter in what order you want to do this. I finished up with 180, so I'm just writing 180. And I'm going to look to my terms. I've got a 2 here, a 2 here, a 3 here, a 3 here, and a 5. So I'm just going to do 2 times 2 times 3 times 3 times 5. And I'm going to do the same thing to this other side. I'm going to list out my prime factors for 144, and that should be 3 times 2 times 2 times 3 times 2 times 2. Go back through your work. Make sure you're noting everything down correctly. Double check. Visually inspect your work. Make sure that your work actually makes sense. Okay? Once you are satisfied with your work, though, all you're going to do is you're going to draw a little box. You're going to write LCM at the top. We are going to then begin crossing out terms that are in common, and we'll write them once to the side. So I have a 2 in common between 180 and 144. I have another 2 in common. I have a 3 in common. I have another 3 in common. Okay. Now we're going to write down once what we don't have in common. What I'm missing is a 5, a 2, and a 2. So my LCM will exactly be 2 times 2 times 3 times 3 times 5 times 2 times 2. And there are a number of different ways we could go about multiplying all of this together, but I like to group things up like so. I'll just do 2 at a time. So 2 times 2 is 4, 3 times 3 is 9, 5 times 2 is 10, and we have 2 left over. 4 times 9 gives you 36. 36 times 10 is 360. 360 times 2 gives you 720. Okay, well, we could double check that. So 360 times 2, I'm fairly certain it'll be 720. 2 times 6 gives you 12, carry the 1. 3 times 2 is 6, plus 1 gives you 7. And so that is indeed 720. All right, for our last example, we will do the LCM of 135 and 55. So using the prime factorization method, we're going to write out the factorization diagram for 135. Now, you should note that 135 is not an even number, so I can't divide 2 into 135 because it ends in a 5. But because it ends in a 5, what students should know is any number ending in a 5 or a 0 is divisible by 5. Any number ending in a 0 is divisible by 10. So 135, because its ending digit is a 5, means that I can take 5 and divide it into 135. 5 goes into 13 2 times. 2 times 5 gives you 10. Subtract. Drop your 5 down. 5 goes into 35 7 times. 7 times 5 gives you 35. Subtract. You get 0. So you have 5 and 27 gives you 135. Now, it turns out that 27 is the same thing as 9 times 3, and 9 is the same thing as 3 times 3. And as you get better at doing these problem statements, as you familiarize yourself with a variety of practice problems, and you just practice this technique, you're going to get better and better at doing prime factorization. It may seem like magic that, like, how does he know what number divides into this? Or how does he know when to do that or when to do this trick or whatever? It's just a matter of practice, guys. Like, if you've done this for 10 years, you get enough practice to where you can do it very, very quickly and very, very efficiently. The same thing is true for 55. We're going to just draw out the factor tree diagram. Now, it turns out that 5 goes into 55 exactly 11 times, which is why we need to memorize our 11's times table if we haven't already. At this point in time, we can write out the factors. 135 will be 5 times 3 times 3 times 3. 55 will be the same thing as 5 times 11. You're going to draw yourself a box. You write LCM. Here again, we're going to cross out any terms that are common. We'll write them once. And then we essentially look for what we're missing. And in this instance, I'm missing a set of 3s. And I'm missing an 11. Group up your terms and just do the multiplication. 5 times 3 is 15. 3 times 3 is 9. 15 times 9 gives you 9 times 5 is 45. Carry the 4. 9 times 1 is 9 plus 4 gives me 13. So I have 135, and then I'm multiplying that by 11. So we have 135 times 11. 1 times 5 is 5. 1 times 3 is 3. 1 times 1 is 1. Drop your 0. 1 times 5 is 5. 1 times 3 is 3. 1 times 1 is 1. Add everything together. 5 plus 0 is 5. 3 plus 5 is 8. 1 plus 3 is 4. And you got your answer, 1485. And that is our LCM. On your papers, especially going into the exam, I need to see all of the work for your problems. Most likely, I'm not going to give you a problem that's more challenging than what you see here. So, I'm going to give you a problem. It's going to have a solution. You're not going to have to divide 10 million into 10 million or whatever. Okay. Okay. I'm not going to give you some ridiculously large problem statement that's overly complicated. If you can do this and master this technique, then you are effectively golden. Now, before I let you guys go, we have to learn one last property of the LCM. The LCM is related to the greatest common factor using the following relationship. So we say the product of two numbers, A and B. I don't know what A is. You don't know what A is. These are just two numbers, are related to the GCF in the following manner. And LCM, I'm sorry, GCF and LCM in the following manner. So we would say that the LCM of two values is equal to exactly those two values multiplied together divided by the GCF of those two values. Now, what this is telling you is you actually don't need to calculate the LCM using prime factorization. Now, you could, but you don't have to. Instead, you could take whatever numbers you're looking at, whatever your A is, whatever your B is, you could multiply those together. And if you knew what the GCF of A and B happened to be, you could then divide by whatever value you happen to be interested in. So, just as an example, let's suppose that we want to calculate the LCM of 36 and 52. What we would do using this formula is we would take 36, we would multiply it by 52, and we would divide that by the GCF of 36 and 52. Okay. Now, at first, this may seem like more work because you're like, well, Mr. Bowman, then I'm calculating the GCF, and what's the point? Or the GCD. And then what's the point? But the thing is, like, maybe students forget how to calculate the LCM because you only have to do it, so many times in the history over the course of your life up through the entire calculus sequence. Like, you probably only have to use the LCM a number of times. But if you remember this relationship, given that you use the GCF much more often than the LCM, you can still find your LCM if you absolutely have to for those few circumstances where it's really necessary. So let's consider finding the GCF of 36 and 52 now. So if we wanted to find the GCF of 36 using the prime factorization method, we're going to first of all say that 36 is equal to 6 times 6, and 6 is the same thing as 3 times 2. So we should have 3 times 2 times 3 times 2. Now, if I want to find the GCF of 52 using prime factorization, 2 times 26 gives you 52, and 13 times 2 gives you 26. Using the GCF, we just need to cross out common multiples. So I've got a 2 and a 2 in common, and another 2 and another 2 in common. So my GCF is going to be exactly 4. Now, we're going to do 36 times 52. 2 times 6 gives you 12. Carry the 1. 2 times 3 is 6. Plus 1 gives you 7. Drop your 0. 5 times 6 is 30. Carry your 3. 5 times 3 is 15. Plus 3 gives you 18. Add everything together. 2 plus 0 is 2. 7 plus 0 is 7. You got 18 left over. So now you're going to have to calculate 1872 divided by 4. Not a problem. We've been doing division forever. So we're just going to go to the side of our page. 4 into 18. That is going to go exactly 6 times. My brain is fried. 4 times. Sorry, guys. 4 times 4 gives you 16. 18 minus 16 gives you 2. Drop your 7. 4 goes into 27. 6. That now goes 6 times. That'll give you 24. 27 minus 24 gives you 3. Drop your 2 down. 4 into 32 goes 8 times. 8 times 4 is 32. Subtract and you get a remainder of 0. So 1872 divided by 4 is exactly 468. And this is, in fact, how you know you didn't mess it up. At the end of the day, if you're doing everything correctly, and you've calculated your GCF in a correct fashion, when you divide the GCF into the product of the two numbers, like we did here, where we divided 4, which was our GCF, into 1872, we need to make sure that we get a whole number at the end of the day. If this was a fraction, we know we've made a mistake. The LCM and the GCF will always, 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 always be whole numbers. They will never be fractions. They will never be decimals. So if you get a fraction or a decimal, something went wrong and you should start over. One last example using this technique. Say we wanted to find the LCM of 74 and 86. We could take 74 and 86, multiply those together, and then just calculate the GCF of 74 and 86. Now, 74 is going to be 2 and 37. 86 will be 2 and 43. Both 43 and 37 are prime, so this is about as far as you can go in terms of a factorization tree diagram. So 74 we found was 2 and 37. 86 we found was 2 and 43. Line your terms up always, always, always when you're doing this. You're going to draw yourself a box. You're going to cross out your like term. You write it there once. There's nothing else in common, so this is my, I'm sorry, not GCF. I should have put GCF. This is my GCF, rather, not LCM, of 74 and 86. So now we're going to drop down to a new line. We have 74 times 86. We're not going to do that multiplication just yet, guys. We're just going to write down a 2. Okay, one step at a time. We will now multiply 74 and 86 together. 6 times 4, 6, 12, 18, 24. Carry your 2. 6 times 7 will give you 42, plus 2 gives you 44. Give yourself a 0. 8 times 4 gives you 32. Carry your 3. 8 times 7 is 54. Plus 3 gives you 57. Add everything together. You're going to have 4 plus 0 is 4. 4 plus 2 is 6. 4 plus 7 gives you 13. I'm sorry, 11. Carry your 1. 1 plus 5 is 6. So now we have 6164 all over 2. Let's just double check this math real quick. This problem should have an answer of start here. All right, guys, suppose we are trying to find the LCM of two numbers such as 74 and 86. Using the GCF division method, we're going to first take the product of 74 and 86. So we're going to multiply 74 and 86 together, and then we will divide that by the GCF of 74 and 86. So we'll go to the side of our paper, we'll determine what the GCF of 74 happens to be. Turns out that 2 and let's say 37 is going to give you 74. And for 86, 2 and 43 will give you 86. So If you line up your prime factors now, you got 2 and 37 gives you 74, and for 86, we have 2 and 43. We're going to give ourselves a little box. We're going to write GCF. Then you're going to cross out whatever you have in common and write it once. So in this instance, we have crossed out a set of 2s because those are in common between 74 and 86, but nothing else is in common. 37 is not the same thing as 43, and so in this instance, our GCF is just 2. Go ahead and we're going to drop down to the next line. We'll do 74 times 86, but the only thing we're going to write is a 2. We're going to insert that 2 in. Now, we're going to go to the side of our page. We now have to do the multiplication of 86 and 74. 4 times 6 gives you 24. Carry the 4. Sorry, carry the 2. 4 times 8 is 32 plus 4 gives you 30. I'm sorry, plus 2 gives you 34. Drop your 0. 7 times 6 is 42. Carry the 4. 7 times 8 is going to give you 56 plus 4 should give you 60. Okay, add a little bit of a brain fart there. 4 plus 0 gives you 4. 4 plus 2 gives you 6. 3 plus 0 gives you 3. And 6364 should be our answer. So now we have 6364 all over 2. And we're going to take 2. We'll divide it into 6364. 2 into 6 goes 3 times. 3 times 2 is 6. Subtract. You're going to drop your 3 down. 2 into 3 goes 1 time. 1 times 2 is 2. Subtract. You get 1. Drop your 6 down. 2 into 16 goes 8 times. 8 times 2 is 16. Subtract. You're going to drop your 4 down. 2 into 4 goes 2 times. And so at the end of the day, you should get 3,182 is your LCM of 74 and 86. Given that there are a variety of different ways to locate the LCM, I hope that students will just stick to a method that makes the most sense to them and keep using that method throughout the course of this class whenever we need it. All right, guys, I'll see you later.